Hello and welcome to JHAPS and World of Ed's lesson on transformation of graphs and functions. This is most suitable for AQA C2 candidates, but Edexcel is also welcome. I think they do it for C1 as well. And GCSE, the A-star topics, you clever people out there. So let's get cracking. The first thing you need to know is that there are four main graphs you need to remember. It's just a matter of remembering them, because without these graphs, well, you're not going to be able to actually do transformation of graphs. So we've all seen this graph before, and this is the graph of y equals x. As you can see, it's very linear, as in it's one big line. Okay, one straight line, and it can go on to infinity as well. And the thing is, it goes through the origin as well, as with all the other graphs that we're about to draw. Another way we can write this, y equals x, is f of x equals x. Okay, the y, you can substitute the y for f of x. And in C1 and C2, you'll see that we mostly just change the y into f of x. So each time you get worried, just change f of x into y or something. So the next graph you need to think about is this graph. It's the y equals x squared graph, and it looks a bit like a parabola, but it's going the other way around. And it basically looks like this, and it passes through the origin, and this part of the graph is symmetrical to this part of the graph, as in if you put a mirror it would look exactly the same. I haven't actually drawn it properly. It will look something like that. What you need to know, that's another way of writing it, is f of x equals x squared. The third graph you need to know is this one. Oh gosh, okay. Okay, that kind of failed, but it's the f of x equals x to the power 3, or y equals x to the power 3. It looks a bit like a snake, or a bit like a sigmoid shape, to be honest. So this is f of x equals x to the power 3. The fourth one, I should have said that there were five shapes that you need to know, the 5 graphs that you need to know more of. The fourth one is this one. It is f of x equals 1 over x. And as you can see, it's not really drawn out properly, but there are all asymptotes over here, the 4 asymptotes. Asymptotes are just basically where a line, where the graph nearly touches the x-axis, but it doesn't. So there's 2 asymptotes, my bad. It nearly touches the x-axis, but it never doesn't. If you do further maths, you'd understand what asymptotes are. So that would be y equals 1 over x, or f of x equals 1 over x. The last one that you need to know, which I forgot to put here, so I'm going to draw it very quickly, is this one over here. It's y equals a to the power of x. GCSE candidates, you don't need to know this. I'm not sure for C1 for Edexcel, but AQA you do need to know this. This is y equals a to the power of x. You need to be wary that this is an asymptote as well. PTOTE. Okay, it comes closer to the x-axis but never touches it. If you do chemistry, you'd come across that as well. Let's get cracking to the next bit. So if we wanted to translate graphs either up or down, left or right, there are special ways in which to write it. So if we do it the GCSE way and we write y equals x plus 2, we would find out that the graph would actually move 2 units upwards. Okay, so let's say that's 2. Okay, so that's 2 units upwards because this is the constant. This is where the y-intercept is. So if you were to write it in a in the A level way, we will write it as f of x equals x plus 2, x squared plus 2. Oh no, I was right, x plus 2. Okay, and so for that one, and for this one over here, if we wanted to move it to on the x-axis, across the x-axis, we can write it as f of x plus 2, say for example, equals x plus 2. Now the thing is with this one is that whenever the numbers are inside the brackets, when we're doing something like this, it's actually like the opposite. It's like a teenager. It does the opposite of what you intend it to do. So x plus 2 basically means that it's moving 2 units to the opposite side, to the left. We're going 2 units backwards. Okay, we're actually going minus 2, and it sounds baffling, but all you just need to do, all you just need to remember is that whenever you have a operation with the x, so for example plus or minus, it does the opposite. So if we have f of x minus 3, it would move 3 places that way. So the main rules of it are the transformation of f of x plus a, with the a outside the brackets, makes a translation, that's 1 mark, of a unit, that's another mark, across the y-axis, or parallel to the y-axis. The reason why we write parallel is because all the points are parallel to the y-axis. If we move them up, it never gets closer or further away to the y-axis. That's why we say parallel. And transformation of f of x plus a, which are all in brackets, means a translation of minus a units across or parallel to the x-axis. Remember, if this is f of x minus a, the translation will be plus a. So for the next one, for translating y equals x squared, the same goes over here. If we wanted to make it y equals x squared plus 3, it would actually move 3 places, 3 units upwards. Or if we were to write it the A level way, f of x equals x squared plus 3, it moves up. It moves upwards 3 places. If you were to write it, if you were to do it across the x-axis, it would be f of x minus 3, for example, and that would equal x squared minus 3. Sorry, that'll be x minus 3 all squared, and it would actually move 3 places this way. Sorry for the messy handwriting there. The rule is still the same for that. For the x, the y equals x to the power 3, the same goes for that. If you wanted to move it 3 places upwards, we move it like that, and it would look like y equals x cubed plus 3, and that would look like f of x minus 3 equals x minus 3 all cubed, and that would move 3 places to the right. And y equals a to the power of x, what we do is that we would actually, which is a bit difficult, we would actually examine the subscript, the superscript. No, it's superscript. We would actually look at the small letters. So if you were to write it as y equals a x plus 3, this is basically telling us that it's in brackets. Okay, so we move it 3 units that way. I know it's a bit confusing. I should have done it on that graph. Never mind. And for this one over here, if it was y equals a to the power of x plus 4, that's when we would move it 4 places upwards. So when it's in superscript, when the numbers are in superscript with x, we move it the opposite way. When it's in normal, when it's just normal, we move it up and down. Again, another thing you just need to learn. And okay, for reflection, I'll come back to the y equals a1 over a. I'll come back to that later. So when we are reflecting this, we would actually write minus f of x in brackets, and that will equal minus x. So if you wanted to plot it, it would actually look like that. If we wanted to plot it, we would just pick random numbers like in GCSE, 1, 2, 3, and we would actually substitute x for 1, x for 2, and x for 3. So if x equaled 1, minus f of x will equal minus 1, and it would go like that: minus 1, minus 2, sorry, my bad, minus 1, minus 2, minus 3. So it would look like this, okay? It would look like a big X. So that's if we want to reflect it in the x-axis. So if you look at it this way, if you have a mirror and you you put the mirror on the x-axis, well, you would actually see that it's actually reflected, okay? And if you wanted to reflect it through the y-axis, what we would do is we will write it as f of x, of minus x, sorry, pardon me, and that would equal minus x as well. And as you can see, it would make the same shape. Okay, again, if you get a mirror and you put it on the y-axis, you would actually see that it all reflects. Okay, so basically what I'm saying, however you write the function of x, when it's linear, when it's y equals x, the reflection is always the same. It can't really be different now, can it, if you think about it? But when we go on to y equals x squared, that's when it becomes a whole different ball game. So if we have something along the lines of minus f of x, and that equals minus x squared. Okay, say for example, the reason why I say this is that f of x equals x squared, right? So minus f of x must equal minus x squared. Okay, it's a bit logical. Now, so if we wanted to actually, anyways, so if you wanted to just check it, we could substitute the numbers in. So for example, we have 1, 2, 3. That will be minus 1 squared minus 1, minus 2 squared, which is, well, minus 2 squared, I should really written it like that, makes minus 4, minus 9. So it would actually look like that. Sorry, again, not really that accurate, but as you can see over here, it's reflected in the x-axis. So this basically flips, and is on the bottom half of the graph. And if we wanted to reflect this in the y-axis, we would write f of minus x equals minus x all squared. Okay, the difference between this and this is that the minus is outside the brackets and the minus is inside the brackets, mainly because this minus is inside the brackets as well. Like, can you see the resemblance? Outside, outside, inside, inside. And if you wanted to do that, if you wanted to reflect it in the y-axis, we can substitute it again. We can substitute 1, 2, 3 into it again. And as you can see, that will just make the same numbers, because minus 2 squared makes 4, minus 3 squared makes 9. So basically what's happening is that this is flipping. It's actually just flipping. I'm not even going to... Let me just see if I can flip it. Yes, I can flip it. Look, it's just flipping in the same way. So it just looks exactly the same. Okay, so that's reflected in the y-axis. If we wanted to reflect y equals x to the power of 3, if we reflect it in the x-axis, we would write it as minus f of bracket x equals minus x squared, right? And that will be reflected in the x-axis. So it would actually be reflected over here, and if I can flip it, it would look like that. It would look like the algebraic x, or 2 cups of water, I don't know. If you just substituted numbers into it, you'd find out that it's still the same. And I'm not still the same, sorry. If we would find out that it would look like this. And if we wanted to reflect it in the y-axis, what we would do is that we would write it as, sorry, not f of x squared, sorry, cubed, because we're on the cubed graph here. We would write f of minus x. Remember, this all just stands for y, so basically it means minus y. Well, that one did, and that would equal minus x all cubed. Okay, all you just need to know is that you just need to remember how to reflect, how to transform, and how to stretch graphs. Remember, the rules are all the same over here. So the last one, if we wanted, this one's going a bit out of depth, but if we wanted to reflect this graph, the equation would be y equals a to the power of minus x. Okay, it's a bit impractical to write a, so if I write 2, so if I substitute a for 2, it would actually be reflected in the y-axis. So if we flip it, so I did on the wrong graph again, sorry, keep on doing that. As you can see, the asymptote is on this side of the graph, and the exponential bit is actually going on the opposite side. Okay, so reflect on the y-axis. If we wanted to, we could reflect it on the x-axis, but we don't need to for AQA, rather. And the last one is stretching. Now the thing about stretching is that when we have a linear graph like this, we can't really stretch it because it goes on to infinity. So we can't really, there's nothing to stretch. Like, I could do that, but there's nothing really to stretch, so it doesn't really matter. But when we come onto stuff like this, when we come onto parabolas, we can actually stretch it. And now the thing is, with having a function as in f of 2x, it's actually referring to that rule that I said. When it's inside the brackets, it kind of does the opposite in which you intend it to. And you would think that this would actually stretch it like you'd actually think that it'll be stretched like this, wouldn't you? But actually no, it's not. It's actually skewed. And the thing is, with math, you don't actually use the word skewed, you just have to say stretched, even though it doesn't really look like it's stretching. So when we have that, it would actually look like this. It will look thinner, okay? It's gone on a diet. When it's inside the graph, it's gone on a diet. And in which to say that is that the transformation of f of ax, so when we're transforming it by f of ax, we stretch it along the x-axis, okay, or parallel to the x-axis, by the scale factor of 1 over a. So for example, if this was 2x, we've stretched it by a half. Okay, remember scale factors in GCSE again. When we wanted to enlarge this by a scale factor 2, it will look 2 times bigger. And that was totally wrong because it started from the same point. It will look 2 times bigger. But if we wanted to stretch it by a scale factor 1/2, it looks half bigger. If that even made any sense. So if we want to actually stretch it, we have to put the 2 outside the bracket, and that means it'll look like 2f of x. Okay, so that would actually be stretched 2 times now. It'll be stretched by a scale factor of 2, and that's what we've written here. Transformation of af of x means you stretch it along the y-axis by scale factor a, okay? This being a. So it will look like afx. That spells facts, that spells affix, if you wanted to know. And the same with these type of things. I don't know why it says reflect on here. If we wanted to stretch it, we would have to have the number outside the brackets. If you wanted to stretch it by a scale factor of more than 1, we'll have to have the number outside the bracket. So that will be f, or 2f of x, and it's just basically saying 2y, isn't it? And it would actually look like, here's my fantastic drawing, it will look like something like that. And if we wanted to stretch it by a scale factor of under 1, we would put the number inside the bracket. So that would be f of 3x, let's say. And that would actually look 3 times smaller. Again, sorry, it will look 3 times, it'll be skewed 3 times, okay? And that is it for transformation of graphs that AQA members need to know. Thank you for watching.